Anything that moves has a wavelength. This was expressed in 1924 by de Broglie, who showed that the wavelength of anything is equal to Planck's constant divided by the object's mass times its velocity. Pretty straightforward. Let's take a nice close look at those units, because if you actually plug in the units that are going to kick in, it may not look like you're going to get a wavelength in meters. I mean, how does a joule times a second divided by kilograms divided by meters per second all cancel out nicely to give you meters? Well, it does work out, but only if you know that a joule is equal to a kilogram times a meter squared divided by a second squared. Replace all that with a joule, and in fact, the units, there's kilograms canceling, etc., do cancel nicely, and you get meters. So fine. Let's do a couple things. Let's take two objects that are moving at 150 miles an hour. That's 68 meters per second. One of them happens to be an electron. Another one happens to be a tennis ball. What is the wavelength of those objects moving? Well, we can just plug in directly. Planck's constant divided by its mass. Don't forget to convert to kilograms, and then the velocity in meters per second, and there's the wavelength of the electron traveling at that insanely small or low speed. Normally it's 300 million meters per second. A tennis ball similarly would have an associated wavelength, but it would be much lower since the mass is much, much higher, and for this the wavelength would be 10 to the minus 34 meters. So this is the de Broglie equation, which gives us the wavelength of just about anything that moves.